On 4.3 problems, I'm going to start with number 3 because I think the other stuff probably isn't worth that much time, but this one does present some interesting points. So this is already arranged in order, but I'm going to explain why it's this order. Now, you would need to do some research and find some KB and KA values, which they don't exactly say. But if we pretend that we did that, we can get some data and then we can arrange this. We know that KNA, NO3, Cl are all parts of strong acids and bases, so they're not going to contribute to the changing of the pH in water. So let's consider the other things. So that's why we have a Kb of Cn minus. It is possible that could draw in some H plus and act as a base. The same goes for the acetate ion. Neither of these, so that's going to be neutral, and the pH would remain at 7. This has no chance of drawing in another H. And I know that some kids will say, but it's minus. You said minus things draw in H, but that's the conjugate base of a strong acid, one of the classics, sulfuric acid. This has basically zero chance of bringing back on its second H. The Ka of that H is spectacularly high. I don't even know what it is. The answer is a lot. So if anything, this is going to no, it's not going to bring one back. If anything, it might give off this one, but not that much. Now, about this ion, I know some kids will say, but it's negative, and you just pointed out that negative things attract H. But consider what negative ion we're talking about once the sodium leaves. This is the conjugate base of a strong acid of H2SO4, so this has just zero chance of drawing an H back onto it, which is why we didn't go looking for a Kb, because the Kb is just like nothing. However, it could donate the second H, and it could, and it really might. That's not a bad number at all for what we consider a weak acid. That's sort of a strong weak acid. It's one of the stronger weak acids, if we can say that. But it would create an acidic situation. So when we look at all these, I'm going to ignore the zinc one for a minute. We get a Kb of this, a Kb of that. So let's compare these two. This is a stronger Kb, so this creates a higher pH than that one. They both create pHs higher than 7, because that's what pH for basic situation is. So they rank in this order above something that keeps the pH at 7 when you add it to neutral water. This creates an acidic situation, so we know the pH is below 7. And the weird comparison is the zinc. And I really had to do some thinking and a little bit of internet sleuthing for this. It says it's acidic, and then some kid, of course, will yell, "You said that acids give off H plus." And then the one to consider And then the weird one to consider is the zinc nitrate. And we cross out the nitrate because it doesn't matter. And I know it says it's acidic, and a kid will be shouting in the brain, "You said acids give off H plus, and it doesn't have any H." That's true. However, this cation could be attracting OH minus, which would remove OH minus from the water situation where it was there naturally from the dissociation of water that happens naturally, and that would change the proportion of H plus to OH minus, which would make it heavy on the H plus because you just tied up OH minus, and that would make an acidic situation, which is why I put it creates an acid solution, not it is acidic, if I can split that hair there. Then I had to go and look up some info, which I just learned myself. So, could zinc attract OHs to itself? Sure. And what I found was a KSP for this. So let's pretend for a moment that we knew we had zinc hydroxide, and if it dissociates, it creates one zinc ion and two OH minus ions. And the KSP for that is very small. It's 3e negative 17. So if we run that backwards, which is what we're talking about, right? We're talking about the zinc taking OH onto itself, then we're running this backward. And therefore, if we flip it end to end, if we reverse it, the K is the inverse of the previous K, which means it's very large. This does a great job of tying up hydroxide. If you can manage zinc cation in water, it will tie up hydroxide ion very well. And I bet it's doing it much better than even this is dumping in H plus. because it looks like it ties up a lot of OH minus, a lot, which makes a pretty darn acidic a situation. So this is being a better base than that one. Both of them are being a better base than something that is neither. This is being an acid, but only a moderately good one, not a strong one. And this apparently is doing a great job of tying up OH minus, and I'll bet it pushes the pH down even below whatever this one achieves. And that's why they're in this order.